Now let's take a look at the next algorithm, which is called model fingerprint. So model fingerprint decomposes feature impact onto a linear, nonlinear, and pairwise interaction effect. So the algorithm was described in Journal of Financial Data Science by Lin, Turkington, Yazdani, and the original paper is called Beyond the Black Box: An Intuitive Approach to Investment Prediction with Machine Learning. So one of the criticisms of uh, financial machine learning is that it is black box. So big investors don't want to trust financial ML because they don't know what are the factors and how actually the model thinks and generates predictions. They don't have the intuition behind it. That they do not understand that it is really difficult to communicate to your investor based on that. So that's why we have um, analyze how feature importance is done. So feature importance is actually the first step to overcome this issue, because when you know what are the most important factors which affect the performance of your model, it really makes your research white box rather than black box. And the second step is to use model fingerprints algorithm to decompose the feature impact on the prediction. So what the algorithm does, as we have discussed, it decomposes feature impact on model prediction into three effects: linear, nonlinear, and pairwise interaction. So what is linear effect? Linear effect means that when you decrease or increase the value of your feature, the probability of positive class, for example, or just the regression prediction increases or decreases also linearly. So in this case, the model, the feature has high linear effect. If very slight modifications of values of your feature lead to extremely high leads to extremely high differences in your predictions. So meaning that if you slightly decrease the value of your feature, but the prediction of your model is modified extremely seriously, so there is a very big change in your prediction value. In this case, the feature has no linear effect. And pairwise interaction effect means that if, for example, if two features, for example, generate value X and value Y, and in this case, there is a very strong difference comparing to a average prediction value. In this case, it means that these two features have very high pairwise interaction effect. So for example, when we try to predict market drawdowns, some of the features um, may have extremely high pairwise interaction effect, like volatility and interest rates, actually, right? So these two features may have very high pairwise interaction effect. So what this algorithm does, it makes a researcher, makes it possible for researcher to take a deeper look into the predictions of our algorithm and understand how feature values actually change those predictions, how our model thinks and generates predictions based on various features values. So this algorithm is very efficient because it also, in the paper, the authors show that, for example, for linear type of models, the nonlinear and pairwise interaction effect equal to zero, because that's actually how linear model works. They don't have linear, nonlinear, and pairwise interaction analysis. They just have only linear effects. So, for example, linear regression, etc. So let's take a look how ML function is used to generate model fingerprints algorithm, and what is the documentation for that. So if you take a look at model fingerprints algorithm, you can see that we have either classification model fingerprint or regression model fingerprint. So what you first do is you set up a model fingerprint algorithm and you need to fit it on your already fit regression model. So you put regression or already fit regression or classifier model, your X, your number of values. So what the algorithm does, it loops through various values of your features to understand how your predictions change. But sometimes if your data set consists of thousands or millions of data points, there is no need to take every value from your data set, but rather loop through quantiles, like take every like first, 20th, and 11th quantile. And in this case, still the efficiency of your algorithm won't change. So num values corresponds to that parameter. So pairwise combinations actually tells what kind of pairwise interaction effects we would like to test for, because the number of combinations on 100 features is huge, and you would like possibly to generate only few of them and test for them. So that's how model fingerprints works in ML Lab package. Now let's go back to the next algorithm, which is called Shapley Feature Importance. So Shapley Feature Importance is a game theory approach applied to estimate the importance of a feature. So the original Shapley approach was motivated by game theory approach. So we have the problem which was solved by Shapley, is that and then it was modified to be solved by in feature importance problem, is that we have a set of features and then they can cooperate to solve the problem of predicting. And based on how well they cooperate, we can generate Shapley feature importance values and understand what drives the algorithm's prediction. So in order to build Shapley feature importance, we use Shap Python package, and the importance of feature I is calculated in the following manner. We get all subsets of features S, so the subsets of features, so feature set is called S, that do not contain Y. So basically we get all combinations of features which do not contain feature I. Then we compute the effect of our predictions of adding I to all those subsets. And we aggregate all contributions to compute the marginal contribution of the feature. So the approach is somewhat similar to MDA. So we try to understand what kind of impact we generate when we take away the information which feature I contains to our data set and measure the difference between the predictions generated with this feature and without this feature. So Shep package is a extremely powerful, and it generates not only feature importance values, but also how various feature values affect model predictions. So if you want to understand and to build the plot of how feature value impacts the prediction of your model, Shapley feature importance and Shep Python package is a clear solution for that. So several useful functions from this package. So the first one is so-called Shapley force plot. So we will show how this force plot works. So basically, force plot decomposes the prediction of one sample. So for example, your model generated a prediction that the label value is 1 with a probability of 80%, and you would like to understand what features contributed most to this prediction and what kind of features were versus that prediction. So probably it is a battle between those features who say for prediction of 1, but some of them say that they are against 1 label. So actually Shapley force plot shows us how this prediction is decomposed on feature level. The second is so-called summary plot, and it shows basically the cool plot of how various feature values change the prediction of our model. The second one is a dependence plot, and what it does, it plots on XY axis the values of your features versus the predictions of your models to build the plots and figures of your predictions versus the feature values, and they also plot the feature which is most widely has the highest pairwise effect with the current feature, to also understand how feature combinations affect model predictions. And as we have discussed, you can use Shapley raw values as proxies to your feature importance scores. So let's take a look at those functions and how they are used on practice. So the first one, what you need is you need to fit in your Shapley model explainer. So here we use Shapley tree explainer. It is a very fast way to get the explanations of Shapley of your tree-based models. Shapley has also a kernel explainer. I think it also has neural networks explainer, but here we use the tree explainer on already trained XGB model. After that, we generate Shapley values out of explainer of xtrain. And in order to get the force plot, we fix the sample for which we'd like to get the force plot. And after that, we build this plot. We put explainer expected value as input value. We put shape values of I. One important note, if you use, instead of classification, instead of regression setting, classification setting, you should use shape values of I and then specify the index of label for which you would like to estimate your prediction. So if you would like to build a force plot of Shapley on impact of your features on the probability of zero class, you should use shape values of I, comma, zero, of I of zero. If you'd like to build the force plot for probability of class 1, you should use shape values of I of 1. So here we pass features for that sample. So xtrain log our sample and the feature names so that we get a clear and beautiful plot. So here we see that the algorithm is a regression XGB model which generated the output value of 658.99, and the base value, so the mean value, is 1,377. So basically, our algorithm generated some somewhat negative prediction. And item MRP was the feature which was the most responsible for that negative prediction. So it drives the prediction of our algorithm from mean value of 1,377 to 658 by the with the biggest scale, right? Outlet years also drive the negative prediction of our algorithm, and only two features like outlet type and item weight were voting for positive prediction. The next plot, as we have discussed, is so-called summary plot, and it basically shows us how the prediction of our model varies from low prediction to high prediction based on various values of our model. But what I personally find is that the dependence plot is the most informative in Shapley feature importance. So as you can see here, we have the shape value, which ranges from negative values to positive values. We have the age value in our data set, and we generate the plot, which shows that the higher the age is, higher the prediction of our model is. What we can also see here is that our feature age interacts mostly with the education num feature, and it uses the heat plot to also plot the values of our education num with age feature, so that we can also not only read this plot in terms of one feature, but also how two features interactions, how they impact the model output. So here we can see that there is a quite strong linear dependence between the age and the positive prediction of our model. And plus what we also generate from this plot is that we can understand how education number together with age move the predictions of our algorithm. So now let's talk about the final feature importance algorithm, which is called line importance. So line framework was initially described in Ribeiro, Singh, and Gustring. Why should I trust you? Explains the predictions of any classifier. So this is some kind of a proxy to a force plot, which is generated by Shapley feature importance. So line, the Python package which uses line algorithm also is also called line. So line is model agnostic algorithm which can be applied to any machine learning model. The technique attempts to understand the model by perturbing the input of data samples and understanding how the predictions change. The output of line is a list of explanations reflecting the contribution of each feature to the prediction of that data sample. So what we do in Lime, we are also able to decompose the prediction of our model on individual feature contributions based on their value. So here our model generated that I think it is mushroom is poisonous for one, and the order stalk surface spore print color and stalk surface below have these features. They have voted for the mushroom being poisonous, and only gill size voted for the mushroom being non-poisonous. And here we can see the values of these features for this sample. So we have discussed how various feature importance algorithms like MDI, MDA, SFI, cluster feature importance, model fingerprints, Shapley values, and line feature importance are used to make our research white box rather than black box. And why it's so important in finance? Because at the end, you need to build a new theory which goes behind your training strategy. And in this case, you can clearly understand when you should use this strategy and when you should stop trading this kind of strategy. So by understanding these factors, you can either improve your model by adding extra features, or what you can do is to understand in what market regimes your model stops working just because this model should not work in this type of markets. And this is why actually feature importance is your research tool and backtesting is not.